Okay. So we have covered the functional principal component, and we know it's very important tools for handle functional data. So now let's move to functional linear model. This is another important topic in functional data analysis. So for functional linear regression model, basically we have to deal with the three different scenarios. So the first scenario is when we have a functional covariates xi or t, and we have a scalar response yi. The second scenario is we have a functional response yit, and we have a scalar covariate xi. And the last scenario is that we have a functional response yit and a functional covariance xi of t. So we will estimate, we will deal with these three scenarios in turn. So first, let's look at the first scenario. So suppose we have a scalar response. So, so in this, here is one example. So basically, I have the 35 cities weather data. I have the delay average temperature for the 35 cities, and we also have the annual precipitations for the 35 cities. So we want to do the predict or find the relationship between the precipitations yi with the delay temperature curves xi of t. So a first idea is that so we have observed the xit, right? So then we can choose some grid of time points from t1 to tk, and then we can evaluate this function xit from t1 to tk, right? And so basically the value of xi at the time tj will be the Jess covariate, right? We have a long covariate, and we can do a linear regression of yi with the covariate xitj. And we do a linear regression. So the problem is that so here how many t1 to tk we should choose, right? So for our examples, we have 35 cities. So so basically our sample size is 35. So if we choose the time too dense, larger than 35 time points, then it will definitely be overfitting, right? Yes, so that's a problem. And so this is the first problem. The second problem is that the value of xi at different time points, at neighbor time points, are highly correlated, right? So we know the temperature today will be very close to the temperature tomorrow, right? So in other words, these predictors xi at tj will be highly correlated. So how can we handle this correlation, right? So we also can imagine that the coefficient beta j will also be highly close, right? So it will be hard to understand that the coefficient to the temperature today will be very different from the coefficient to the temperature tomorrow, right? So that's another potential problem. So if we increase the time continuously, make it very dense, then we know that this summation will become an integral. So So this summation beta j times xi tj will become the integral of beta t times xi of t dt. So in this case, we will don't have to worry about to choosing the time points, right? And also here we in the models we only have two parameters, alpha and beta t. So so looks like we are not overfitting. And also you can see when we're using integral, it kind of handle the functional predictor xit very naturally, right? Okay, so this is a functional linear model. First functional linear model we will learn. So this model is also called a Scalar-on-Function linear model because the response is the scalar and the predictor is the function. So we will estimate the parameter alpha and beta t by minimizing integrated square error. Okay, so we will estimate alpha and beta t by minimizing this integrated square error. Although here we only have two parameters, alpha and beta t, we know that beta t actually is infinite dimension, right? So so theoretically, if we allow the beta t to have completely free function, then we are able to find a very vigor function beta t such that the fitting will be exactly, the fitting error will be equal to 0. This will be overfitting problem, right? So we have to control the smoothness about the beta t. As I mentioned before, so we believe that these xit are highly correlated. So the coefficient to the xit beta t, the coefficient to the temperature today will be very close to the coefficient to the temperature tomorrow. So we want a beta t to have to be changed very smoothly. We don't want a beta t to change too much, right? A big idea in functional data analysis when we estimate the function is that we will represent the function beta t use a basis expansion. So beta t will written as a linear combination of basis functions. So phi1 to phi j t will be basis functions. C1 to Cj will be the basis coefficients. Okay, so we will choosing the basis functions in advance, and then we will estimate the basis coefficient C1 to Cj. So here I give you a short introduction about the basis functions. So basically, we will have two types of basis functions. One is a Fourier basis function. So this is the formula for the Fourier basis functions. Okay, so here omega is equal to 2 pi over p. P is the period of oscillation. So you can see here when we have the Fourier basis functions, the sine cosine function will appear in pairs, right? So plus we have always have the first basis function equal to 1. So the number of Fourier basis function will be always be odd number, okay? So this is to show you how the Fourier basis function looks like. The second popular basis functions is called a B-splines. So here, this is graph is show you cubic B-splines. It's also the most popular B-spline base function we use. So basically here, you can see that so each of the color of this curve is one basis function. So if you look at this red function, or maybe this black function in the middle is a bell curve, right? And so these basis functions, black basis functions, is only non-zero in 1, 2, 3, 4 intervals. And this vertical lines is the location of the nodes. Okay, so B-splines is defined by the order and the nodes. So first we need to define the location of nodes. So here, from 0 to 1, I defined 11 equally spaced nodes. And then so we choose the order. So here for cubic B-splines, order equal to 4 is basically the degree plus 1 order. And so basically for each of these one basis function, B-spline basis function, this black one is one basis function. So it is non-zero at 4 adjacent intervals. And also in each subintervals, it is a cubic, piecewise cubic polynomial function. So basically, the cubic B-splines will join these 4 cubic polynomial functions smoothly in the node location. Okay, so here, each of these basis function is only non-zero up to 4 subintervals. So this is the summary for the splines. So basically, splines are polynomial segments joined end to end, and in these segments, in this joint point, this polynomial function is constrained to be smooth. Smooth means the function is continuous. The derivative is also continuous, and so this segment joint point is called a knot, and the order of the splines is equal to degree plus 1 of the polynomials. So we define the order of the polynomials and also the location of nodes, then we define the B-splines. So this is kind of, you give the ideas for the B-splines with different order. So this is order equal to 1. Okay, so order equal to 1 means that in each segment, it's a degree 0 polynomials, so it's constant. Okay, so this is order 2 B-splines. So in each segment, so in each basis function, each segment is a linear function, linear polynomials, and so it's non-zero at most 2 segments, and most of the degree, the order segments. So order 2 means at most 2 segments. So this is the order 3 splines. So in each segment, it is a degree 2 polynomials. This is order 4 B-splines. Each segment is at most order degree 3 polynomials. So we can also have high order B-splines. So the number of B-spline basis function is equal to the order plus the number of interview nodes. So if we know the order of the B-splines, And if we know the number of interval knots, we will know the number of basis functions. And the derivative of the basis function will be up to m-2 be continuous. Okay, so for example, if we choosing cubic B-splines, the degree will be m equal to 4. The degree will be up to the second derivative to be continuous. Okay, and also the B-spline basis functions are positive over at most m adjacent intervals. So if we have cubic B-splines, the B-spline basis function will be a positive over at most 4 adjacent intervals. This is called compact support properties. So, this is a very key feature for the fast computation, even for thousands of basis functions. And we know that the sum of all B-splines is equal to 1, and most popular choice is order 4 cubic B-splines, means continuous second derivatives. So we know that the cubic B-splines is decided by the location of the knots and the order. So basically, the order will be chosen depend on what derivative of the function you want to estimate. So if you just want to estimate the function itself, you will choosing so basically you will choosing the cubic B-splines. Okay, so basically if you want to choosing interested the first derivative, you will choose order 5 B-splines. So if you're interested in k derivatives, you will choosing the order of the spline to be k plus 4. So we generally we will fix the order of the splines, and we will vary the number of knots when we do the estimation. So the order of the splines does not change the results a lot. Okay, so generally we don't recommend to choosing too high order of splines. Okay, so for example, we very unlikely to choosing order greater than 6 B-splines, because order 6 B-splines means you are choosing degree 5 polynomials. So these high order polynomials can become very unstable. So we only choosing low order B-splines. And we can increase the flexibility of the basis functions by increasing the number of knots. So generally, the knots are equally spaced. So there are two important rules. So generally, we will put more knots when you think the function has a sharper change or a strong curvature, and we will put less knots when the function changes slowly. If you know the function is a constant, you will put less knots there. And generally, we will require at least 1 data point in each interval. And so a rule of thumb is that we will simply put a 1 knot at each time point with observation, and then we add the roughness penalty to control the smoothness of the function. So this is the summary of the B-splines. Okay, so now it's 2:21. Okay, so we have learned about the B-splines. So we know B-splines is defined by the number of nodes, location of the nodes, and the order. And so we recommend that we simply put one node at each point of observation, but we adding a roughness penalty to control the smoothness of the function. So we will express beta t as a linear combination of the basis functions. So here, phi j are basis functions, and cj is the basis coefficients, and we can also write down as the vector form, phi transpose t times c. Okay, so with this expression, we can plug the expression of beta t into this formula, and so then we can, because the basis coefficient c does not depend on t, so we can put a c outside the integral. And so here, basically, we assume that we know xi of t, and we have defined the basis function phi of t. So therefore, we are able to calculate these integrals numerically. So suppose this integral is defined as zi. So then we can treat zi as a known covariate, and then we can write down the model as a linear model. And we have parameter alpha and c here. So then we can estimate the alpha and c by least squares. So here c is known, we can calculate it, and y is the observed response. So this is the results when we estimate the functional linear model on the temperature data. So yi is the annual precipitation, xi is the delayed temperature. So here we using 11 free basis functions to represent beta t. And so this is the estimated beta t. And so you can see here that beta t is going up and down kind of randomly. And it is very hard and frustrated to know what this beta t stands for, right? Yes. So that's the reason, because here we don't have any smooth control on the beta t. We kind of doing an overfitting here. If you think about, if using 11 free basis functions, 11 plus the intercept, you actually have 12 parameters to fit 35 data points. So you're a little bit overfitting. Okay. So the key thing here is that we want to add the roughness penalty. So we want to control that beta t is a smooth function. Okay, so what we will do is that besides this sum square errors or the fitting errors, we will add in a roughness penalty. So so here you can see that the roughness penalty for beta t is defined as the second derivative of beta t, taking the square and taking the integral. So lambda is the smoothing parameter. It's kind of control the smoothness for the for beta t. Okay, so then we can redo the algebra, and so we first write the f beta t as a linear combination of the basis functions, and then the second derivative of beta t can also be written as the summation of the second derivative of the basis functions, right? So So this is very convenient. So then the roughness penalty defined by the second derivative of beta t can also be written as this quadratic form. So basically is a C transpose times R times C, and this R is a J by J matrix is equal to the integral of the second derivative of the basis functions times the transpose of the second derivative of the basis functions. Okay, yeah. So this R can be calculated numerically very easily. So we will know R. And then we can write down the penalized sum square errors in vector form. So basically, we plug in the formula for the beta t as a linear combination of the basis functions. And we still put the basic coefficient C outside the integral. And then we defined Zi as the integral of basic function phi t times the observed curve xit. Then we do the least squares, and we will find out this basis coefficient C will be equal to Z transpose Z plus lambda R inverse times Z transpose Y. And so here you can see that this R is a J by J matrix. And so if this R is an identity matrix, then this will become just the ridge regression, right? So you can see that this roughness penalty actually is very close to the ridge regression. Okay, so this is the estimated basis coefficients. So after we get this basis coefficients, then the fitted values for y we write as y hat will be equal to z times c, right? So we plug in the formula for c here. So basically, we defined all these terms before y to be S. We call S as the smoothing matrix. Then the fitted value y will be equal to the S multiply the data y. So S is the smoothing matrix. Okay, and so y basically is a projection matrix projecting the observed value y to the smoothed value, the value of the smooth function. So after we get this smoothing matrix, a nice thing is that we can define the effective degree freedom by using define as the trace of this smoothing matrix S. Okay, so you can do some algebra that when lambda equal to 0, then the trace of S is equal to capital J. It's a number of basic functions. Okay, so in other words, this effective degree freedom represent the effective number of basic functions used. Okay, so when lambda equal to 0 means we have capital J basic functions. When lambda is greater than 0, then the effective number of basic functions will be reduced. So this is how we define the effective degree freedom. So then we can choose in the cross validations. We can choose in the smoothing parameter lambda by minimizing the cross validations. Okay, so this is the definition of the ordinary cross validations. And so you can see here S sub Ri is the diagonal element of the smoothing matrix S. And also we can, using another criterion called generalized cross validation, or GCV. And so this is the definition for GCV. And you can see it's a little bit different from the ordinary cross-validation. It's a little pretty similar, but a little bit different. So trace of S will be equal to the summation of SII. Okay, so we can estimate the smoothing parameter by minimize the cross-validations. And so here, for these examples, we see the cross-validation scores is minimized when lambda equal to 10 to 12.5. Okay, so so generally, when we choosing the grid points, we estimate the lambda, choosing the lambda by set a grid search on the grid points of the candidates on the smoothing parameter values. So generally, the smoothing parameter, when we design the grid points for the smoothing parameter, we will using the log scale. So because you know, the smoothness will not change too much when you change lambda to from for example 1 to 1.1, right? It will be very similar. So instead, we will choosing vary the value of the smoothing parameter by scale. So we can choosing 0, choosing 1, 10, 100, 1000, right? So we will make a kind of big change on the value of the smoothing parameter. Okay, so so this is the results when we using the roughness penalty to fit our temperature data. So the response is the annual precipitation. The predictor XIT is the daily temperature. So so here we're using 35 Fourier basis functions. So it's a lot of basis functions, and we choose a smoothing parameter lambda to be equal to 10 to 12.5 by minimize the cross-validation. And so this is the estimated beta t. So you can see here the estimated beta t is much smoother, right? And you kind of will get some ideas how this temperature related to the annual precipitations. Basically only the data. So the temperature after so this is around 250, 220. So we'll be around around August. So you can see here the temperature from August to January will have a positive effect on the annual precipitation. The reason because if you have a warm winter, you tend to have more precipitations than the cities with a colder winter. I'm not sure. I think we may have general ideas that you know, if a city had a warm winter, probably it will have a lot of rains and a lot. So if a city is cold, probably it will have a lot of sunny days, like a very sunny and very cold days. Okay, yeah. So this is the results. So you can see that after we adding a roughness penalty, even we're using a large number of basis functions, we can still get a pretty smooth estimation on the beta t. So here we have 35 Fourier basis functions, but you calculate the effective number of parameters, which is the trace of the smoothing matrix, is only 4.7. So in other words, when we using 35 Fourier basis functions, when we add in the roughness penalty, we only have effective 4.7 number of basis functions. Okay, so this is a very good way to control the model complexity, right? So this is another thing I mentioned before, that you know, when we choosing the using this roughness penalty method, we can control the number of basic function to be any values, right? But if you just choosing the number of nodes, then your number of nodes, your number basic function can only be an integer, right? So it cannot be 4.7 number of basic functions. Yeah. So this is the reason I highly recommend you when you develop a method or use the method, try to choosing the method with roughness penalty. That is much easier to use and also more flexible. So this is the how the prediction looks like. So you can see here, we have what the x-axis is a predicted annual precipitation. The y-axis is observed annual precipitation. And so most points is, so this red lines is a y equal to x. And smooth point is around this line, means the prediction is pretty good. They are not exactly on the line, so we don't have overfitting problem. So now let's look at the confidence intervals. So basically here, this is the formula for the basic coefficients, right? And so then we can calculate the variance of the basic coefficient using the what we learned for the multivariate statistics. Basically, is this matrix times the variance of y times the transpose of this matrix. So if we assume that the variance of y is RID with variance sigma square, we can take the variance of y equal to sigma square in the front. Okay, and so we can estimate the sigma square by using the standard sum square error divided by n minus the degree of freedom. The degree of freedom is the effective degree of freedom we calculated, is equal to the trace of the smooth matrix. So then we can come with the confidence intervals for beta t. So this is the dashed lines are the confidence intervals for beta t. And so you can see here for most time points, the confidence intervals cover 0, means they are not significant. Okay, so the beta t will only become significant positive after around day 240 or 250. So it's after August, so from September to the winter. Okay, so so the reason is because, as we just mentioned, that generally if we have a warm fall and winter, we will have more precipitations. Okay, so so here we define the roughness penalty by look at the second derivative of beta t, right? So so when we want the second derivative equal to 0, means the linear function will not get a 0 penalty, right? And so if we wanted the function to be periodic, then as we learned before, we may define the harmonic acceleration operator. So basically, if we define the harmonic acceleration operator, then the sine cosine function will receive 0 penalty, right? So we will give no penalty to the sine cosine function because they are very smooth, right? So when we estimate a beta t for periodic functions, we were using the harmonic acceleration operator. Okay. So we have learned this functional linear model, and response is a scalar, and the predictor is a function. And we learned how to estimate beta t by a roughness penalty, right? And so when we you can see that for this functional linear model, the key part is this beta t, right? This beta t represents the cumulative effect of xit on the yi. So based on the complex intervals, we identified that the temperature will have a significant positive effect on the precipitations. So the summer, the temperature in the summer will have no effect on the precipitation. So when we present to our collaborators, sometimes they still feel a little bit confused. Not everybody feel comfortable to using these confidence intervals to to define this significance of the beta t, significance of this effect. So this kind of motivates us to think about, is it possible that we can estimate the beta t that it is non-zero, will become, beta t will become strictly zero when xit has no effect on the y, and the beta t will only become non-zero when xit has a significant effect on the yi. So in other words, we want this beta t to be zero in some intervals. Okay, so so this motivates us to develop a locally sparse estimator for functional linear regression model. So basically, here you can see that the first term is the sum square error of the fit. The second term is the roughness penalty, and the third term is the Scalar penalty. This is we call a functional Scalar and penalty, and we developed. So here P lambda is a Scalar penalty function proposed by Fan and Lee in 2001. So if you don't know what the Scalar penalty, Scalar function looks like, so this is the Scalar function is, okay? So basically when the u is away from 0, the penalty will become constant, okay? So so we kind of propose this functional Scalar penalty. This is how the functional Scalar penalty looks like. So basically, this functional Scalar penalty can be viewed as the limit of the average of the Scalar penalty on the norm of beta t at each subintervals from tj-1 to tj. Okay, so basically here we want to look at the norm of beta t at each subinterval, and we try to squeeze this beta t to be equal to 0 in this interval. Okay, so this is the functional penalty, Scalar penalty looks like. So we have shown that this functional Scalar penalty can have oracle properties. So if the true beta t equal to 0, then beta hat t will be equal to 0 with probability 10 to 1. And so the null regions, which means the beta t, the region when beta t equal to 0 will be consistent by our sloss estimator, our estimator called sloss estimator. And if for each t, when true beta t not equal to 0, we will also have the asymptotic normality for the beta hat of t. So this is one simulation study. So basically, we do this functional linear regression model on two functional covariates, x1i, x2i, and we estimate beta 1t and beta 2t by our sloss estimator. So the true beta 1t is 0 from 0 to 0.5. The true beta 2t is 0 between 0 to 0.4 and between 0.8 to 1. Okay, so now we will use our sloss estimator to estimate beta 1t and beta 2t. So this is our estimation looks like. So you can see here for the beta 1t, it is true beta 1t is 0 from 0 to 0.5, right? So if we look at the beta 1t from 0 to 0.5, you can see that only our sloss estimator is strictly equal to 0 in this interval. For ordinary least squares or the smooth estimator means we only add in the roughness penalty. They always non-zero in the whole 0 regions. Okay. So similar for the beta 2t. So the true beta 2t is 0 from 0 to 0.5 and from the region from 0.8 to 1. So for our sloss estimator, we are able to identify that this function equal to strictly 0, generally accurate in the 0 regions. We only little bit non-zero when it connected to the non-zero regions because we want this function to be smooth. So when it's smooth, it kind of will force this function to go up a little bit. And this is the summary for the estimated beta t. And so you can see here, our sloss estimation has the smallest root mean square error, okay, and much smaller than the smooth estimator and the ordinary least squares. So the Oracle smooth estimator is that is the estimator when we know, we assume we know the true 0 regions. Okay, of course, in real life, we can never using the Oracle estimator, we never know the true 0 regions. Okay, so you can see that if we our estimator actually very close to the Oracle estimators when they know the true regions. So this is the results on the clean and weather data. So our response 1i is the annual precipitation, and the xit is the daily temperature, and so we want to estimate beta t. So so here the red one is our sloss estimator, and the blue lines is the smooth estimator. And so you can see here that our smooth sloss estimator will be strictly equal to 0 from January to September. So only October to December will have a 0, will have positive values. So it means that the temperature will have a positive effect from October to December, and on the precipitations, and the temperature from January to September will have no effect on the annual precipitations. So this is consistent to our previous results. And so you can see the smooth estimator will be 90 at any points. So it's hard to interpret the smooth estimator. So so you can yeah. So far we only cover the functional linear model with one functional covariate, and so it is possible to have multiple functional covariate. So if we have multiple functional covariates and scalar covariates, this will be this model looks like, and we can still doing the penalized, minimize the penalized sum squares, and sorry, this should be minus, and then we have a roughness penalty on the beta JT, and so in that case we will express beta JT as the linear combination of the basic functions separately. So we write down all these basic coefficients, and alpha, gamma is a coefficient to the scalar covariates as a big long vector of the parameters, and we calculate xij equal to the integral of xij t times phi jt dt. So this xij can be calculated, and then we write down a long vector zi equal to this scalar covariates zi and also this xij. And we can calculate the smooth penalty matrix Rj is a j by j matrix. Then the estimated parameter will also looks like the similar form as before. And so this is the estimation. So here is the summary of our estimators. So basically, we introduced the Scalar-on-Function linear regression model. This model moved from the summation to integral, right? So it's very easy, very naturally handle the functional covariates. So to make the control of the smoothness on the functional coefficient beta t, we add a roughness penalty to do it. And we also can come with the confidence intervals based on the residual errors. The results can generalize to multiple and mixed covariates. Okay, so this is our introduction on functional linear regression model.